Welcome students, welcome to Physics and Chemistry Made Easy. Today our topic is about Vernier Calipers. It's an instrument which can measure a minimum distance of 0.1 mm accurately. Now coming to Vernier Calipers, what is the difference between Vernier Calipers and the scale what you are using in the class? You know this is called ordinary scale. The minimum count is 1 mm. That means you can measure a distance accurately up to 1 mm. You cannot measure a distance accurately which is less than 1 mm. So what does this 1 mm mean? It means that it is its least count. Least count means the least distance which can be measured accurately using any equipment is called as least count. So this is called ordinary scale, and the least count of this scale is 1 mm. That means the first reading, okay, this much it is 1 mm. That is the least count of this scale, ordinary scale. Now coming to Vernier calipers. This is Vernier calipers. Okay. It has got two scales. This one is main scale, which is also called as ordinary scale, and two jaws are fitted to main scale. These two are the two jaws fitted to the main scale. These two are called immovable. They don't move because they are fixed to the main scale. Now coming to the other one is what? A Vernier scale. A very interesting scale this is. This one is a Vernier scale. This is a Vernier scale. And two jaws are attached to Vernier scale. One is on the top and one is below. And Vernier scale is movable. Vernier scale is movable. See, it is Vernier scale which moves, not the main scale. And the next one is two jaws are on the top. These jaws, these upper jaws, and these are called lower jaws. Upper jaws are meant to find internal diameter. Suppose say I want to measure the internal diameter of this pen cap. So I have to bring the jaws closer to each other. Fix this jaw. Fix these upper jaws into the pen cap. And I have to pull it back. Now see, it doesn't fall down because I have pulled it from the inside. So I am now measuring inner diameter of this pen cap. Similar to that one, if I want to measure the length of this pen cap, if I want to measure the length of this cap, then I have to place it here. Okay? It's like this. These two jaws are meant for finding out external diameter, you can say, but what I have used here is length, external diameter of a pipe and all that, external. Now these two jaws are called internal jaws, these two are called external jaws. These two jaws are fixed to the main scale and these two jaws are fixed to the Vernier scale. It is Vernier scale which moves, not the main scale. Now coming to its calibration, count. This is called main scale. This is similar to your ordinary scale. And the least count of this main scale, since I told you that it is similar to ordinary scale, the least count of this scale is 1 mm. It is 1 mm. Now how John Paul Vernier has designed Vernier calipers, let us see. Vernier calipers is different from Vernier scale. This part of the scale is called Vernier scale. All together, everything put together, it is called Vernier calipers. It has got one more thing, this one, strip. This is used to find depth of the cylinders, okay? Depth of the cylinder, like that. Okay, very good. Now coming to this, I will tell you how this is designed. And on the whole, the least count of this instrument is 0.1 mm. How do we get 0.1 mm? That means 1 mm is divided into 10 equal parts. That's a very interesting thing. To look at 1 mm measurement only we find very difficult. Then how is it? It is easy to take down the readings. At the same time, the design is an extreme different. Vernier calipers consist of two scales. One is main scale. Just now I told you, this is the main scale. This part is called main scale. Similar to what scale what we are using in the class, okay? Ordinate scale. The least count of this scale is how much? 1 mm. That means it can measure a distance accurately up to 1 mm only. Less than 1 mm, this cannot measure a distance which is less than 1 mm accurately. Accurately means correctly. Therefore, we go for an instrument called as Vernier calipers. This part of the Vernier Vernier calipers has got two scales. This is main scale and this is Vernier scale. Now this Vernier scale, how this Vernier scale is designed, now let me tell you. So when you speak about ordinary scale, this is your ordinary scale. So first division is 0, then it's 1, 2, 3, 4 and this is 5 mm, 6, 7, 8, 9 and 10 mm. 10 mm means what? 1 centimeter. Okay, 1 centimeter. So how did he develop Vernier scale? Vernier scale. He took 9 mm. He took 9 mm. Only 9 mm. Only 9 mm. 9th mm it is. So 1, 2, 3, 4, 5 mm, 6, 7, 8, 9 and 10, which makes 1 centimeter. So he took 9 mm, 9th mm, and he divided this 9 mm into 10 equal parts. So he divided this 9 mm into 10 equal parts. This is called Vernier scale. Now when you divide this 10 equal parts, it's like this: 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. This is 10th one. Just divisions. This is 9 mm. This total is 9 mm divided 10 equal parts. In this design, there is an interesting thing. These are 10 lines, okay? The first one is 0, this is 0, so 0 to 1, 1, 2, 3, 4, okay, let us consider this as 5, then 6, 7, 8, 9 and 10. So what happened in this, no? One division from this, that means among these 10 lines, one line of Vernier, I'm making it clear, one line of Vernier will exactly coincide the main scale division, So let us see which one is exactly coinciding, which division of Vernier is exactly coinciding the main scale. Let us see. First one, no, it coincide in the sense like this. Okay, first one is not coinciding, second one is not, third, fourth, and then fifth one, sixth one, seventh one. According to me, I myself took like that. So just to explain you, the seventh one is exactly coinciding the main scale division. Now you need not worry to which division it is coinciding on the main scale. You need not worry which division on the main scale is coinciding Vernier. No, you need not worry this one. You have to worry about Vernier scale division. Which Vernier scale division is exactly coinciding the main scale division. So here it is 7. So that is called VCD, 7th division. So that is called VCD, Vernier coincidence division. Verniers, only Verniers, coincidence division. So you need not worry. It is actually what? 5, 6 and 7 mm. You need not count this one. No worries with this one. We have to just look into which division of Vernier is coinciding. Why am I repeating again and again? Because this is the logic in this instrument. So that is called VCD. Now let me continue. So this part is over, right? Now let me design least count of this Vernier calipers. So it has got its one principle. It follows a principle called as n-1 mean scale division is equal to n Vernier scale division. n-1 mean scale division is equal to n Vernier scale division. This is a principle of Vernier calipers. Now let us take main scale, MSD means main scale division, right? Let us take it as S, and VSD means Vernier scale division. Let us take it as V. So now what happens? n-1, since I already told you MSD means S is equal to n into V, because VSD is equal to V. So let us multiply n into s is ns, minus into plus is minus s is equal to nv. So let us bring nv to this side and let us take s to the other side. Therefore it is s here, ns minus nv, because nv has come this side, so it has turned into negative 1, and negative s has gone to the other side, so it is plus 1. Now n is common, so n into s minus v is equal to s. Therefore let us send n to the other side, so it becomes s by n. Now s minus v is nothing but least count. That is the formula, least count. S minus v is least count, because s is MSD, main scale division, and v is Vernier scale division, is equal to s by n. What is s? 1 main scale division. S is 1 MSD. MSD, as it is already stated here, MSD. S means MSD. What is n? Number of Vernier scale divisions. Number of Vernier scale division. It's not, see what I took here, V, it is V, VSD, Vernier scale division is V. I didn't speak about N now. N is number of Vernier scale division. Now coming to this least count, let us try for the formula least count. So LC, least count, is equal to 1 MSD minus 1 VSD. 1 MSD is how much? 1 mean scale division is how much? 1 mm. Number of Vernier scale divisions are how many? 9 mm is divided into 10 equal parts. So let us go for LCM, 10. 1 goes in 10 times, 10 into 1 is 10, minus 10 goes in 10 one time, therefore it is 1 into 9 is 9. So 10 minus 9 is how much? 1 mm by 10. So your answer is 0.1 mm. This is the least count of Vernier calipers. And in centimeters it is 0.01 centimeter. Now when to take millimeter and when to take centimeter, it all depends upon your main scale reading. It all depends upon the main scale reading. Now let me draw the diagram of Vernier calipers and explain you how to take the values. So Vernier calipers has a main scale. This is a main scale. It has a strip to measure the depth of cylinder strip. Now a jaw over here. It's like this. Then you have inner jaws. Yes. Okay, this should be perpendicular. This part should be perpendicular. It should not go across, perpendicular to this line. Okay, done. Now when I draw the main scale readings, 0, 1, 2, 3, 4, and this is fifth one. 6, 7, 8, 9, 10. Like this is 1 centimeter. Now again 1, 2, 3, 4, 5. 6, 7, 8, 9, and this is 10. This is 2 centimeter. 1, 2, 3, 4, and 5. 6, 7, 8, 9, and 10. This is 3 centimeter. Right. It goes on. It's a big scale. Just for the explanation, I took this much. Now coming to Vernier scale. Vernier scale. This is Vernier scale. All put together it is Vernier calipers. This is called Vernier scale. Right. Draw equal to this one. Right. Finished it. So it's like this. Yes. This is Vernier scale. So this is 2 centimeter. Very good. Now what shall I do? I have to see, this is an opaque, isn't it? Steel one. So you can't see the readings which are back of this metal strip, isn't it? So you have to rub down. What are the readings which are back of this? So it is, how much it is? 1.5, 6, 1.6, 1.7. Here you find 1.8, 1.9, and this is 2 centimeter. Okay, done. So you will find yes, jaw. One more jaw on the top. These two are called internal jaws to measure the inner diameter. These two are called external jaws to measure the external diameter at the same time. So you have placed an object to measure the length. So it can also measure length like this it is. Now vernier division, let us see. It is starting from here. Vernier scale. This is vernier scale, not the calipers. Okay. All put together it is called vernier calipers. Now this part is vernier scale. What did I tell you? 9 mm is divided to 10 equal parts. Right. So 0, it is 0 over here. Then 1, 2, 3, 4, 5. 5, fifth one. Okay. Then 6, 7, 8, 9, and this is 10 over here. 10 divisions. Right. So this is called vernier scale. Good. What is this called? Main scale. This is called main scale. Right. How did you design vernier scale? You took 9 mm, what we say, this is 9 mm, isn't it? Like that, 9 mm divided into 10 equal parts. Finally, what is your least count? Your least count in millimeter is 0.1 mm by the formula. LC is equal to S by N, and in centimeter it is 0.01 centimeter. Now you kept an object, you want to know the length of this object. Now what is really important, you know? Suppose say you are measuring the length of this object. See, I want to measure the length of this object. I can do it with the help of ordinary scale. So I kept ordinary scale which we are using in the class, ordinary scale, this scale. Now what happened is the reading is here, say, imagine the reading has come up to here. It is say 2 centimeter, and the next one, the reading 2.1 is here. Okay, done, 2.1 is here. So the object length, this is the object as I told you. The object length is what is happening to the object length. With the help of this ordinary scale, you cannot give the accurate reading. Why? Because the final bit of this object, is lying between 2 centimeter and 2.1 centimeter, 2.1. See, once again I will show you a bigger one. So this is 2 centimeter and this is 2.1. Okay. What is here I am telling you. What is here? Now your object has come up to here. That means either you have to say 2 centimeter approximately or 2.1 centimeter approximately. See, you are using the word called approximately. Why you are using the word approximately? Because you have a little bit. I am showing it bigger one. Actually it is not that big. It is very small. See, this much only. It is neither 2 neither 2.1. It is lying between these two. Little bit this part. To know this part, the length of this part accurately, we are using this vernier calipers. Because your ordinary scale can measure up to this 2, you can say 2 centimeter approximately or 2.1 centimeter approximately, that's all. What about this piece of the object? Therefore, we are going for vernier calipers. Now we will see how vernier calipers can measure this small amount of length that is left over between 2 centimeter and 2.1 centimeter. So now start. So what happened is, there is a formula to measure this length. MSR, L is equal to MSR plus VCD into LC. Main scale reading plus vernier coincidence division into least count. So what did I tell you? MSR, taking MSR is actually very important. Now see, this is vernier 0. This is vernier 0. Okay? This is vernier 0. Now this vernier 0, I will draw a little bit big. I will draw a little bit big and show you. This is vernier 0. Main scale, this is main scale 2. What is here I am showing you, what is here I am showing you little bit big. Vernier scale 0 is lying like this. Next reading 2.5, 2.1 is here. So your Vernier scale as the reading 0 is lying between these two, 2 centimeter and 2.1 centimeter. Okay, then how to take MSR? Whatever it is in the front of Vernier scale, that should be taken as MSR. How can you take 2.1? Because your object is coming up to here, it is up to here only. It is not going to 2.1. Therefore, this whatever is front of Vernier scale, that should be taken as MSR. So what is MSR here for us? It is 2 centimeter and this part is 2.1. This part is 2.1 and this part is 2 centimeter. This part, let me tell you, this part is 2 centimeter and this one here is 2.1 centimeter. But my Vernier is lying between these two. So same thing I showed here. It is lying between 2 centimeter and 2.1. So I should take this as MSR. So my MSR here is 2 centimeter. Since I took centimeter, you should understand that the least count in centimeter is 0.1. Right, depending, because I just now mentioned here, right? Now what is next one? VCD, Vernier coincidence division. See, I told you previously also, this is called Vernier scale and there are 10 divisions over here. 10 divisions are present over here. Don't worry about main scale reading. It's over now. Main scale reading you need not worry. Once you take MSR, you need not worry about main scale. But the thing is what? There are 10 divisions on Vernier scale. One division among these 10, okay, one division will exactly coincide the main scale. That is called VCD. Now which one is coinciding? Let us see. This is first reading 1, okay, 1, this is 2, 3. I said it is 3. For me it is 3. I kept it like that. So it is third division is exactly coinciding. Now to which number it is coinciding on the top, you need not worry. You need not worry about MSR. Only thing is among these 10, which one is exactly coinciding the main scale. This is main scale reading. Now main scale readings are like this. Vernier first division is like this, okay? And now whatever among all these 10, one will exactly coincide the main scale. So mine is third one. So my VCD is equal to 3 into least count. Therefore now reading is what? 2 remains as it is, 2 centimeter. First thing in Vernier Caliper, screw gauge and all that, interesting thing. First you have to multiply this part. So it is what, how much? 0.03. And then this should be added to this one. So it is what? 2 centimeter and 0.03. Therefore your answer is 2.03 centimeter. Excellent, isn't it? See, with your naked eye, the length of this object is 2, pakka 2, and it is lying between 2 and 2.1. So it is not 2.1. From the answer, it is not 2.1. That means you are able to measure this extra, this little bit which is extra, this length. It is lying between what? It is lying between 2 and 2.1. 2 and 2.1. So you didn't go for 2.1. Your calculations also don't show 2.1. You are able to measure this amount of length accurately. This little bit which is between 2 and 2.1, you measured and said that it is 0.03. So on the whole, the answer is 2.03. It is not even 2.1. Yes, exactly. It is not 2.1 there. So you got that extra length, that little bit of length. You cannot measure it with an ordinary scale. It's not possible to measure with an ordinary scale. Therefore, you have done it with the help of Vernier calipers. Vernier calipers has got 2 scales. One is main scale, which is a simple ordinary scale. With the least count is 1 mm. It's ordinary scale, not what we are using in the class. But the design is this one. This is an excellent design. He took 9 mm from the main scale. He took 9 mm from the main scale, right, and divided this into 10 equal parts. Whichever is coinciding the main scale, that he took it as VCD. That's why this formula plays a great role. Now I'll explain you zero errors. No zero error. See which scale is moving? Vernier scale moves, not the main scale. So main scale 0 you have to take it like this. Right? Main scale is not moving, main scale does not move. Main scale reading. Main scale division or reading. Main scale, yes, exactly. And what is that moves? Vernier scale moves. Suppose say it's like this. So you should start the definition from here. It is easy actually for students to remember. It starts from here. If the 0th division of the Vernier scale exactly coincides, you see, you should start from this side and you should start from this side. Definition, I am speaking from definition part. If 0th division of the Vernier scale exactly coincides the 0th division of the main scale, then it is said to be no zero error. As such, where is this error? No error. If the 0th division of the Vernier scale exactly it is coinciding, the 0 division of main scale, then it is said to be no zero error. So if you want to find the length of the object, then the formula will be MSR plus VCD into LC. That's all, because there is no error. Next one is what? Positive error. Positive zero error. Right. As I just now told you, main scale 0 does not move. Main scale does not move in Vernier Calipers. It is Vernier scale which moves. So positive error means like this it is. What? If the 0th division of the Vernier scale is on the right side, we say this side means it is right side. If the 0th division of the Vernier scale is on the right side of the 0th, again start from here, 0 division of the main scale, then the error is said to be positive error, positive zero error. And the correction is negative. Correction is negative. So positive error, negative correction. So the formula L is equal to what? MSR plus VCD into LC. This part of the formula remains same. Positive zero error it is now. How it has become positive zero error? Because it is on the right side. Vernier scale 0 is on the right side of the main scale 0. So the correction is what? Negative. Therefore it is taken as minus n. Corrections are represented with n, minus n. Why? Because positive zero error, correction is negative. Now we'll speak about negative zero error. As I was telling you, main scale 0, main scale does not move. It is Vernier scale which moves. Come forward or go back. So if suppose like this it is. So I told you to start definition from here. These are just to say that you start definition from here, these symbols. If the 0th division of the Vernier scale is on the left side, it's on left side, 0th division of the main scale. You should just start. These symbols have to just tell you that definition. You can start definition from here. It is very easy. If the 0th division of the Vernier scale is on the left side of the 0th division of the main scale, then it is said to be negative zero error and the correction is positive. Right, and the formula is L is equal to MSR plus VCD into LC. This is a common formula. For negative zero error, therefore correction is positive. Now what I want to tell you is very simple. If you are asking the students to remember it like that, okay, there are few who can remember. You can even give them an idea. You are asking the students to go to the ground and stand, and before that you have drawn a line. Imagine that you have drawn a line. You are asking student not to cross that line. So a good obedient student did not even touch the line. He is a bit back of this line. So we feel very good for him. Right? We feel very good for him. So he is positive attitude. So positive zero error. Now you have drawn a line in the ground and you ask the students to go and stand just beside, do not go across the line. Now what happened? Few students went across the line. It's quite natural that what happened, you will get angered because they have crossed your line. So you can treat them as negative. You can treat them as negative because you will get anger, isn't it, like that? So this is something about zero errors.
Like